Chaudhary, a rising sophomore at Monte Vista High School. Today, I want to go over a continuity of piecewise functions. So why don't we head on into it? Now, before I want to get into this, what I want to do is explain to you guys more of what a piecewise function is. A piecewise function is kind of, you can think of it like a Frankenstein, where you're kind of sewing up multiple different functions together to create kind of one massive function. So let me explain to you what I mean in this case. So here we have a function, f of x. It's kind of like the overarching function, where they have two separate mini functions inside of it. Now over here we have a point, 2. Now this is essentially where the kind of stitches for this function are, because this is where the two different functions meet up. And this is what I like to call a Frankenstein point. So what we want to do in order to find the continuity of a piecewise function, before I get on into that, let's discuss what continuity is. Continuity is when your graph can be drawn without lifting up your pencil or pen, and it doesn't have any, let's see here, let me explain. It doesn't have any vertical lines, it doesn't have any jumps, and it doesn't have any sharp edges like that. Or in that case, even a removable discontinuity can cause a function not to be continuous. So that's our goal. That's what we're trying to find in this video, but we're trying to find it of a relatively more tricky function for more students to grasp. So why don't we head on into it? So continuity for any function would mean that the right-hand side of it and the left-hand side of it and the point itself are equal. So we use limits to find this out. So we're going to call it the left-handed limit, and the right-handed limit is equal to the right-handed limit, and it'll also have to be equal to the point at which it's at, which you'll understand a lot more when I actually do the problem. So the left-handed limit is, so if we have this graph over here and we have this as a point, the left-handed limit is the limit from the left side, and the right-handed limit is the limit from the right side. So why don't we head on into actually solving this problem instead of going over all of that. So x squared minus 3 if x is less than 2. Now this is kind of like its condition. And 2x minus 3 if x is greater than or equals to 2. Now one thing I can notice about these functions individually is that they both are continuous. But when they both are together is kind of the problem we're trying to look for. So x is equal to 2 is our Frankenstein point. So that's the point we're going to take our limit at. So we're going to go limit as x approaches to 2 from the right side. And the right side in this case is this bottom function over here, because it's greater than or equals 2. So we're going to go limit as x approaches to 2 from the right side of f of x, which in this case is 2x minus 3. Now, in order to calculate a limit, just remember a limit is getting infinitely close to the number it's going to, but it won't exactly be that value. But us as mathematicians, we like to plug in that value to find out what it's approaching. So we're just going to plug it in here too. So 2 times 2 minus 3, and that's going to equal to 4 minus 3, which is 1. So now we're going to do the same thing except from the left side. Limit as x approaches to 2 from the left side. Now these are the ways you denote whether it's from the right side or left side or not. So this is from the left side, and that leaves us with this function over here, which is x squared minus 3. And x squared minus 3, and we can check that right over here, anything less than 2, which means from the left side. We're going to plug this value of 2 in again. You're going to get 2 squared minus 3, 4 minus 3, and that's 1. Now, this ensures us that our limit exists. Sure, the graph will be something like this. Our limit exists. If this is the value of 2, this and this are both approaching the exact same point. But we're not quite sure about the actual point itself yet, because that itself could be a removable discontinuity. So what we want to do in this case is we're actually going to plug in the value of 2 for whichever function is applicable. So now we're going to find f of 2. And if this is equal to both the limits, then the function is continuous. So in this case, if we want the value to equal to 2, we're going to use the second function over here because its x is greater than or equal to 2. So then you're going to plug in the value for that, 2 times 2 minus 3, which is equal to 1. So in this case, the right-handed limit is equal to the left-handed limit, and it's also equal to the actual value at the point. So in this case, this function is continuous at x equals 2. Now I'm writing x equals 2 because we're not sure whether, if let's say this piecewise function had more conditions to it. Like in this case, we know that it's continuous everywhere else because the functions itself are continuous, but we'll just leave it at it's continuous at x is equal to 2. So now we're going to move on to f of x is equal to these three conditions, x squared minus 6x if x is less than 3, 0 if x is equal to 3, and 5x plus 3 if x is greater than 3. Now here they're nice. They already gave us our value at the point 3, which is also our Frankenstein point. And we have our two different main functions. So basically, if we want the function to be continuous, both the limit from the left and right side would have to equal 0. So why don't we head on into it? So we're going to find, the limit as x approaches our Frankenstein point 3 from the right side. The right side is going to be this bottom function over here because it's for all values greater than 3. So we're going to do 5x plus 3. We're going to plug in the value of 3, 5 times 3 plus 3, which is equal to 15 plus 3, which is 18. Now we're going to do the same thing for the left side. Limit as x approaches to 3 from the left side of x squared minus 6x. And this is going to equal to 3 squared minus 6 times 3. Now 3 squared is 27. 27 minus 18. 27 minus 18 is 9. So we could already see the limit doesn't exist, which already signifies that it's not continuous. And overarching all of that, it's not equal to 0. So right-handed limit is not equal to left-handed limit, and it's not equal to the actual point itself. So function, we could just write is not continuous at x is equal to 3. And we're going to move on to our next problem, where I kind of changed up the scenario here, and instead of giving us one Frankenstein point, we're going to have two different ones. So why don't we take a look at the problem? F of x has three conditions. The first one being x minus 1 is x minus 1 for x is less than 1, 3x minus 3 for 1, which is less than or equal to x, which is less than or equal to 3, and the last one, which is minus 4x plus 2 for x is greater than 3. Now these are all continuous normally without it being stitched up. So what are we going to do in order to actually find whether this function is continuous? Well, because we have two Frankenstein points, we're going to have to find the left-handed limit and right-handed limit for both those Frankenstein points, and then find the value at that point and kind of do the same process that we did here except twice. So let's go for the first Frankenstein point at x is equal to 1. So let's go ahead and find the left limit as x approaches to 1 from the left side first. So from the left side we have x minus 1, because these are for all values less than 1. So we can have x minus 1 here, which is going to equal to 1 minus 1, which is equal to 0. Now what we're going to do is we're going to find the limit as x approaches to 1 from the right side, which is this second function, which is x is greater than or equal to 1, because we're not focusing on the 3 over there. So x is greater than or equal to 1, and we're going to do it for this function over here. So 3x minus 3. When we plug in the value, you're going to get 3 minus 3, which is also equal to 0, showing that our limit exists. Now we have to find out whether it's continuous or not. And for that, we all know that we're going to have to find f of 1. Now, between these two functions over here, this one is valid for plugging in the value because it's x as it's equal to or greater than or equal to 1. So if we plug in the value, it's going to be the same as the right-handed limit. 3x minus 3, which is equal to 3 minus 3, which is equal to 0. So for the x equals 1 case, we can see over here that the value, this portion is continuous. Now we're going to have to do the exact same thing, except for x is equal to 3. So, what we're going to do now is we're going to find limit as x approaches to 3 from the left side. And from the left side is this function again, 3x minus 3. You're going to plug in the value of 3. 3 times 3 is 9, 9 minus 3 is 6. So you're going to get an out value of 6. You're going to do the same thing for the right side. Limit as x approaches to 3 from the right side, giving us this function, minus 4x plus 2 is equal to, you're going to plug in the value of 3. Minus 4 times 3 is minus 12. Minus 12 plus 2 is minus 10. And from this, we can already see that the limit doesn't exist. Therefore, this portion of the function is not continuous. So, if we can still test it out and plug in x is 3. X is equal to 3. F of 3. But you're just going to get more proof. For f is equal to 3, for x is equal to 3, you can use this function again. And you're going to get a value of 6 coming from there. And this part of the function is not continuous. This part of the function is continuous. Not continuous. So that's all we have for this video. Yeah, we have 3 separate types of problems, introducing you to the Frankenstein points and in some ways the Frankenstein function. And I hope you guys enjoyed this video and learned something, and hopefully this will help you out on your SATs, ACTs, and AP classes. So do subscribe to the video and like it if you haven't already, and thank you.